Hello and welcome back to the ViDiLabs Academy. In this video lecture I will talk about colors. We have to go back again to the human eye in order to understand better how we see colors in television. Everybody of us has seen a rainbow either after the rain or perhaps using a split prism in experiments of physics at school, where white light shining on a prism is being split, or if you want, decomposed to the basic primary colors that white light contains, which is actually the spectrum of all the colors that human eye can see. Colors are very important and complex issue in television, and certainly the same applies to CCTV. Colors offer valuable additional information of the object being viewed, and sometimes color alone can be the decisive clue about determining an intruder or stolen car type, for example. It is also found out, very importantly, that human eye captures color information quicker than the fine details of an object. So, as already explained in the previous lectures about human vision, the colors we see are actually various wavelengths of light. Our senses, the cones which are picking up colors, are picking up certain wavelengths, and we recognize them in color, but what the cones are doing are actually picking up electromagnetic radiation of different wavelengths. So how we see colors of the objects around us? Basically, every object that has got a color is actually the wavelength that is reflected by that object, and we pick it up as such color. For example, if we have a red piece of paper, the pigment with which the paper is painted red is the frequency or the wavelength that is reflected from that paper when white light shines on it. If we have white piece of paper, that white piece of paper will reflect all of the wavelengths, which we will see as white because white sunlight is being shone on it. And equally, if we have a black piece of paper, then black will absorb most of the colors and we don't see any, so we see black, which is why black is actually, any black object is usually getting warmer because it absorbs all the wavelengths, as opposed to white, which reflects most of them, which is why they're colder relative to the temperature that is outside. Now, it has been found that using only 3 primary so-called colors, by mixing them with different intensities and strengths, we can replicate almost all colors that human eye can possibly see. And this is the basis for color mixing, both in printing industry, in painting, in television, of course in CCTV as well. So before we go any further and explain how human eye works in order to find the relation to how primary colors in television have been created, I would like to say a couple of words about the types of color mixing. So in fact, there are 2 types of color mixings, which are different, but we don't think about their differences, but they are done in completely different ways. This is so-called additive color mixing, which is typically generated by media that generates light, like television, your phones, smartphones, anything that produces light will use additive color mixing model to produce different colors by having 3 primary colors, red, green, and blue in this instance. Now, why they're called additive? Because we add colors to produce the resultant color. And when we add all 3 of them, red, green, and blue, the resultant color is white. So adding the colors produce brighter objects, and we are mixing them. Different to that is subtractive color mixing. So the difference here is we are not producing light. We are not generating light to see the object of interest, but we're actually using incident light that shines on a piece of paper, on a canvas painting, and we are seeing the reflected light from such a media. And because of that, in order for us to see colors, we actually mix the colors, but we are getting darker as we mix them. So if we add all of the colors in subtractive color mixing media model, we will get black. So mixing more colors getting darker rather than brighter. And this is simply because, like explained just a little bit earlier, the colors, for example, yellow is a white light shine on a piece of paper that is painted with yellow pigment, then all colors are absorbed by that pigment except the yellow. The yellow is reflected and we see it as yellow color. The subtractive color mixing primary colors are not the same as additive color mixing. So we have cyan, magenta, and yellow there used as a primary colors. While they are slightly different, the idea is the same, to produce any color visible by human eye by mixing of these three primary colors. In fact, in subtractive color mixing model, especially when we're talking about the printing industry, most magazines being produced by subtractive color mixing will add to the cyan, magenta, and yellow, even though they would be sufficient to produce most of the colors. They still cannot produce the very dark tonalities and really black. So a black color as such is added to the cyan, magenta, and yellow. And you probably would know that the printing industry would require CMYK model. Like if you are having a photograph and you're preparing a color book or magazine, then you need to produce CMYK version of what you see on your screen, which is RGB version. So there are two different color spaces, and it's very important to understand that they can never be the same. They can be approximated, but it's very difficult to produce on print exactly what you see on your computer. This is done by careful color management of the color space of the printer as well as the monitor and match them. Then when you know what color transformation is happening, you can produce something that looks very similar on paper as what you have on your screen and other way around. But again, there are two different color spaces. So back in the 19th century, near the end of the 19th century and beginning of the 20th century, there has been a lot of pioneering scientific work on finding out how human eye works, how colors are being seen. Based on those works by many scientists, International Commission on Illumination was formed, the so-called CIE. And in 1931, they were the first to define the quantitative links between distributions of wavelengths into electromagnetic visible spectrum and physiologically perceived colors in human color vision. They are basis for mathematical relationship that were formed later on, which we use even today in defining color spaces, in understanding how television produces colors, how printing makes colors, and the differences between different color spaces. As we can see on this graph here, they describe the three different types of cones that are found in the human eye, which in a way are sensitive to certain portions of the spectrum. They have not clear cut between different colors, so red, green, and blue, for example, as shown here, but in actual fact they sense quite a bit of a bandwidth between blue around the main frequencies of green and red, and in fact the red is not really red as we know it in television, but it's actually more orangish, so it's closer to green than to red. However, these are the statistical finding of the various experiments, many of which have done very good work. And on this diagram, actually, we have a normalized sensitivity of all three different types of cones. S is for the short wavelength, which corresponds to the area close to the violet. Is depicted with blue line, but that's close to violet. The M refers to the medium spectral wavelength, which is around the green color. And the L is for the long wavelengths, which is around the sort of orangish, yellowish orangish color, but it's depicted here with red line. So These are the so-called 3 stimuli colors. So 3 different colors that are picked up by 3 different cones in human eye. As we said, the retina has cones and rods, but out of the cones there are 3 different types, which actually combining their sensitivities and response to different wavelengths produce all the colors that we see in our brain. So in fact, really it is the brain that produces all these different pigment excitations, and the mixing of colors is still quite a complex science, and maybe not so clear even today, but for us it's important to know that this is a starting point for creating this color space of CIE 1931, where we see the normalized spectral sensitivity of human cone cells. Now, we did mention, but we'll just reiterate again, different species than human may see completely different spectral range. Like I mentioned in the human vision section of the video lecture, we have rats or cats that see in the infrared, birds are seeing in ultraviolet, bees the same. So there are different species that have adopted the evolutionary survival with different sensitivity of different parts of the spectrum, which is not necessarily identical to human. What we are discussing in television and CCTV is human eye sensitivity, and this is standardized in the CIE 1931 spectral response of each cone of human eye. So the importance of the CIE work is in their devising the color space, the human vision color space, which is shown here, and it looks like a horseshoe-shaped curve. This horseshoe-shaped curve shows at the periphery of it the purity, the pure colors, which are shown here as wavelengths in nanometers, starting from about 380 nanometers to close to violet color, all the way through 400, 500, 520, down to greenish, yellowish, orange to 700 nanometers. So the shape of this curve is a little bit out of the scope of this video lecture to explain how that came to be, because it includes a lot of mathematical transformations between how human cones pick up the colors and how reference colors that were used to simulate any color in between were tested, and how we actually, with 3 possible primary colors, can produce any color in between. But this is an effort that actually is a good starting point for what television used later on, to use 3 primary colors, red, green, and blue, with particular wavelengths to reproduce all that they can within this horseshoe-shaped curve. Now, the idea in this is that any 2 points of colors in this chromaticity diagram can be reproduced by putting together, by putting a line between the 2 wavelengths, and anything in between can be formed by mixing these 2 colors. For example, if we have a 580 nanometers, kind of orangish colors, and let's say take 490 nanometers. So if we make a line between 490 and 580, the idea of this is that any color that sits on that line can be produced by mixing certain proportion of 490 nanometers and 580 nanometers. So in fact, any source of color that can be made, the less the better, but obviously you can't produce all colors with just 2 basic colors. You need to have at least 3, and if those 3 colors are used, then any space in between can be reproduced. So that depends on what humanly possible colors, man-made, artificially generated colors, can be found to reproduce these colors. So for example, we have something called sRGB space, which most of you have heard of, and the sRGB space is used in the ITU BT709 recommendations, which is part of television. Hence, it's part of the compression algorithms, and it is also part of what we use in CCTV. For example, that space defines the red color as x coordinate to be 0.64. So here is the x 0.64. And the y coordinate is 0.33. So this is the source of light for the red, 0.64 and 0.33 for the y. This is the reference source of light for red in the sRGB space. Then we have the green color is generated by wavelength that sits on 0.3 of x and 0.6 of y coordinate in the CIE color space. So this is representing the green possible reproduction by sRGB space. And then we've got the blue, which sits on 0.15 at x value and 0.06 at the y value. So using this sRGB triangle, all colors that fall within this triangle are reproducible. So clearly there are a lot of them that are out, but a lot of them that human eye can see as different tonalities can be reproduced. Similar idea is for let's say Adobe RGB space, where the actual colors of red and blue are the same as the sRGB space, but only the green color is used in the region which is defined by the NTSC in the past, which is roughly about 0.2 over something of x and about nearly 0.7 of a y. While if you compare with this the CIE RGB space, as we said earlier, which was shown in this diagram, remember we had for the blue 435.8, for green 546.1, and for red 700. With using such a color space of CIE, we've got this curve sitting 546 was here, that was the green color. The 700 nanometers was the red color, and about 435.8 nanometers was there. So CIE RGB space is slightly bigger, but again, these are the colors, especially on this bottom part, that cannot be reproduced using the technology we use in LCD screens, for example, or OLED screens. So this explains how the colors are used in television and how three primary colors can be used to reproduce almost all visible colors that human eye sees, but certainly not all literally, but a big portion of it is reproduced by combining three primary colors, which is the basis for seeing color in television. So from this can be seen that given any three real sources of colors, we cannot cover the gamut of human vision. There are no 3 points within the gamut as shown here that form a triangle which includes the entire gamut. The gamut of human vision is not a triangle, it's wider than that. So in practice, this means that colors produced in television, computer screens, or digital cinema, for example, can only reproduce a portion of the spectrum that human eye can see, but not all colors. So television, computers have limited gamut, which is always within the CIE horseshoe-shaped curve. In other words, man-made color spaces used in computers, television, and CCTV are only attempting to reproduce real-life colors, but can never reproduce all that we experience in our eyes in real life, all that we experience with our eyes in real life. This is why we have different color spaces, depending on what are the primary colors, how it was created, and what is the transformation of red, green, and blue values to the display. Many factors influence this, including the media-owned embedded color space, the operating system gamma, whether it's Windows, or Microsoft, or Mac OS, or Linux. They also have certain gamma that handles the colors. It also depends on the encoding, decoding color space conversion in the compression and decompression and so on. So all color video screens, whether that is a plasma display or LCD or OLED, they all produce colors by using three primary components: red, green, and blue, with certain wavelengths, and mixing them at different intensities reproduces all the possible colors that gamut, that color space can produce. This is a magnified view of liquid crystal display screen. As you can see, they're always aligned next to each other, red, green, and blue. And again, controlling each one of them separately, individually, all the colors in that gamut that this LCD display is able to show are going to be reproduced. In LCDs, we have light that comes from behind the screen, and that light these days is usually in the form of LED, very white LED that actually is blocked by the liquid crystal of red or green or blue intensity. So the pigments are red, green, and blue, and applying electricity makes those red, green, and blue less or more transparent, making the white light come through only the pigment of red or green and blue with higher or lower intensity, and combination of those reproduces all the colors. In the past, the concept was the same. The only difference was we had phosphor coatings on the cathode ray tubes, on CRTs, and these phosphor coatings were producing predominantly red or green or blue color. We had so-called red, green, and blue electron beams, which were really not colored electron beams. They were just simply electron beams, but when they were hitting these phosphor coating areas, each one of them was producing the primary colors of the phosphor coating type. Therefore, from distance, these three colors, these three primary colors and intensity are mixed in our eyes, and we see the resultant color. So here is shown a magnified view of that. So you can see that even though this screen from very big distance may look like light bluish, when you magnify it and come close to it, you will see that actually that is reproduced by having all red, green, and blue lit more or less with the same intensity, so that from distance that looks like whitish. Obviously it's not as strong here because it's only magnified image, but the idea is that mixing from distance is seen as resultant color. Similarly, the top part, which looks like reddish, maybe orangish more than reddish, you will see magnified is basically only red and green phosphor element lit, the blue is off, and that from distance looks like orangish color. Okay, very often in television, CCTV, and photography, the term color temperature is used when talking about light sources. So color temperature refers to the temperature to which an imaginary perfectly black body is heated up and consequently produces light. This is from the theory of physics, which states that the spectrum of light generated by heating is mostly dependent on the temperature of the body and not on the material. That's a very important statement from physics. It was proven by the physicist Max Planck, whose formula explains the relationship between the peak wavelength radiated and the temperature to which the body is heated up. This formula is shown in this graph as lambda maximum equals 2896 divided by the temperature in Kelvin degrees. So that means if we have a body that is heated up to 3400 Kelvin degrees, imagine a very hot lava, perhaps, the peak temperature, the peak wavelength at which this heated body radiates is lambda m equals 2896 divided by 3400. And that will give you what is the wavelength in nanometers of that particular body. So every different temperature, whether it's 2400 or 2900 or 3400, has certain peak that shifts. So the hotter the body, the black body is, the closer this temperature is towards visible light and goes in fact towards the bluish. the colder relative to the 3400, the colder it is, the peak goes away from the red color into the infrared, which is the portion of the spectrum where the heated body radiates its heat. Now, it can be seen that the peaks for different temperatures are outside of the visible spectrum, which are above 700 nanometers. This is why I illustrated here with a visible spectrum, what eye sees, and as you can see, that's very small compared to the wavelengths of the longer wavelength of radiated heat, so we can only see up to about 700 nanometers. Heat is nothing more than infrared light, as we know, and the higher temperatures for tungsten lights cannot be used because the melting point of tungsten is around 3500 Kelvin degrees. So increasing the temperature to more than 2800 or 2900 will dramatically shorten the lifetime of the tungsten light. So in today's globes, the air is extracted from the inside of the bulb in order to minimize the burning of the filament. But as we know, tungstens are used less and less, and more we have LEDs. But the terminology of color temperatures originates from the time when we were talking about tungsten filaments, which were heated up to this temperature of 3000 degrees or maybe a little bit less. So in the past, for accurate camera testing, a specific light source of specific temperature, color temperature, was defined, so that we know that at different temperatures we've got different amounts of lumens produced per watt of energy. For example, in the past, photographers or even cinematographers could use the relationship where it says that a 500 watt tungsten light, for example, that was heated up to 3200 Kelvin degrees, produces approximately 27 lumens per watt. The 200 watt tungsten heated up to 2980 Kelvin degrees produces approximately 17.5 lumens per watt. And a 75 watt tungsten light heated up to 2800 degrees approximately produces 15 lumens per watt. If you remember when we discussed about the different sources of light defining lumen, which is radiometric and photometric units, we did mention about lumens versus the wattage, but really this refers only to the tungsten lights. LED lights, LED lights, and fluorescent lights produce different amount of lumens per watt because of a different method of producing the illumination, rather than a tungsten filament heated up to high temperature. So in CCTV, one of the problems that we have as opposed to human eye operation is that the camera does not have understanding of what source of light you're using. So engineers had to design automatic white balance correction. So this is an algorithm in the electronic processing of the image where the camera looks for the brightest part of the image and then assumes that brightest part to be white and then corrects it according to the its internal lookup table that it has, knowing what are the combinations of red, green and blue components in order to produce such white. And by such a correction, it is achieved a white balance correction. So that means if we didn't do that, image taken at a tungsten light will appear yellowish reddish. Most people would remember that from the time of film in film cameras, even though it can be similar can happen even today with digital cameras, but most digital cameras will automatically correct it with such electronic circuitry. In the past, films did not have such corrections, so you were supposed to know what kind of filter to use to correct the tungsten light, which was yellowish reddish, to appear as normal light. And similarly, if you took a picture with a film camera in the past that has got fluorescent light, which will appear greenish if not corrected, you know what filter to use to correct that. So in electronic cameras, which include CCTV, Such correction of color is done by electronic circuitry called white balance. Now, in the very beginning, most CCTV cameras have the so-called automatic white balance, which is AWB circuitry, that adjusts its color's temperature automatically upon powering up the camera and seeing a large area with white content. So the typical operation in the past was that before you turn on the camera, you put a white piece of paper in front of the camera, a paper that is illuminated by whatever light you've got around, but that paper has to reflect white light towards the camera. As soon as you turn on the camera automatically, the first thing it does is checks what is the color temperature of that image, how much it is shifted to one or the other side, and the camera electronics automatically does automatic white balance adjustment. So the camera, once it's shown a white piece of paper, adjusts itself so everything looks normal to our human eye. Now, today's camera are a bit more advanced, so we now have automatic tracking white rather than AWB. We now have ATW. So automatic tracking white is basically constantly adjusting this depending upon where the camera looks at. This is a very important adjustment for faithful color reproduction. When you have pan-tilt zoom cameras, you may be in a situation where pan-tilt zoom camera looks outside, for example, and you've got a certain color temperature from the daylight. The color will be adjusted according to that, but as soon as you turn the pan and tilt towards the inside of a building, perhaps in a car park, where you've got predominant man-made artificial light, which could be fluorescent, it could be tungsten, it could be LED, it doesn't matter. It is different source of light in that case to what was while you're looking outside. And ATW will check again automatically as soon as the picture changes and readjusts its own white balance to reflect what is normal to human eye when you're looking at different color temperature source of light. So the purpose of the white balance, automatic white balancing and automatic tracking white, is to make the image that the camera picks up be similar to what human eye can see it. And obviously we do not care about such adjustment in our eyes because our brain adjusts that automatically without us even knowing this is happening. It's like we discussed about focusing, we discussed about iris working in human eye. Similarly, the brain is the one that automatically adjusts and corrects the color temperature irrespective whether we read a book on a daylight outside where the sun is shining on the book, or we read the same book inside with tungsten light or with fluorescent light. Our eyes automatically make that book appear white papers if it is white paper in the background. So again, white balance for us is automatic as a human vision instrument, but for the CCTV and any video image processing industry, photography, cinematography, white balance is very important, and the essence of the white balance is in color temperatures understanding, which is the essence of correcting by the sensor and electronics based on the shift that an image gets relative to the white perceived by such a camera. The color temperature of the electromagnetic radiation emitted from an ideal black body, as per the theory, is defined as its surface temperature in Kelvin degrees, as we saw earlier with some of the examples. The color temperature is closely associated with human eye perception because we base our experience of colors from the visible light. And for most light sources, this is not the actual temperature of the surface. The exception is the incandescent lamp, where the color temperature in fact corresponds somewhat closely to the radiation of some black body. The incandescent lamps with tungsten filament, for example, produces light by way of thermal radiation, and the lamp approximates an ideal black body radiator. So its color temperature is essentially the temperature of the filament. But other light sources, such as fluorescent lamps, LEDs, emit light primarily by different processes than thermal radiation. So their emitted radiation does not follow the form of a black body spectrum. These sources have so-called correlated color temperatures, and it is the temperature of a black body radiator which, to human color perception, most closely matches the light from the lamp. The CIE 1931 color space graph is shown here, and is showing chromaticities of black body light sources for various temperatures. So as you can see, it starts from somewhere deep red, showing as 1500 Kelvin degrees, going through oranges 2000, 2500, yellowish nearly 3000, 4000, 6000, and the higher the Kelvin temperature, color temperature goes, the further away from red is and closer to blue. This is only the actual human perception of it, not the actual temperature of the surface body. For example, for the sun, we know that the effective color temperature, as seen from the surface of the Earth, is about 5780 Kelvin degrees. So as we all know, the sun appears red or orange at sunrise or sunset, but that doesn't mean the temperature on the surface drops down to 5700 degrees. It is the appearance from the Earth surface to us based on the experience that we have from the visible light only. The changing of the color of the sun during the day from red to orange, yellow, and almost white bright is mainly a result of the scattering of light through the atmosphere, and is not due to changes in its black body radiation. So that's an important thing to understand. The blue color of the sky is caused by so-called Rayleigh scattering. Rayleigh, which is the scientist that explained that, and the scattering that is appearing from the molecules in the atmosphere from the sun actually produce that appearance of blue light. And similarly, the same happens when the sun is sun rising or sun setting. We've got a predominant long wavelengths or closer to red, and this is why we see sunsets and sunrises to be red in color. The daylight has a spectrum similar to that of a black body with a correlated temperature of about 6500 Kelvin degrees. This is also known in the lighting and photographic industry as a D65 viewing standard. That's a little bit more complicated for this video lecture, but it is important to know that there is some reference in the industry called D65, which corresponds to the black body with a correlated temperature of 6500 Kelvin degrees, which is equivalent to a daylight. Let's now show the actual color temperature spectrum, so we can explain how these different colors or color temperatures fit in our everyday experience. We'll start from the very low. This is shown as a spectrum from red to white, going through all the colors. It's only symbolic, of course, but the closer to red is, the lower the temperature is. The higher, the closer to blue and white is. So at the very bottom of this spectrum simulating the color temperatures in Kelvin degrees, we've got a 2000 Kelvin degrees, which is approximately the color temperature in a natural world of a sunrise or sunset. Human-made candle produces similar color temperature. As we go higher with the color temperature, we're coming to a man-made illumination of the past days, mostly now with tungsten lamps. They range from anything about 2800 Kelvin degrees for, let's say, 100-watt tungsten lamp, up to about 3200 Kelvin degrees for flood lamp. We did say previously that different wattages produce different lumen intensities, which can be used to calculate the amount of light you have, but the color temperature of tungsten lamps mostly is around 3000 Kelvin degrees. This is the reason, as we said earlier, of appearing reddish yellowish color when you take a picture with old film cameras. So if you don't have a filter, blue filter to correct that, all images done in indoor with incandescent tungsten lamp will appear about yellowish reddish. Electronic cameras do white balance correction, as we said earlier, and this is the first important color temperature to remember for us in CCTV at least. 3200 Kelvin degrees approximately is the preset for indoor white balance on some cameras. That is a setting that you can access in most cameras via the menu. And I would suggest to think about this, especially when you have projects where you may want to see, let's say, money, color of the money, or even playing cards, although money would be more critical, let's say, in a bank or where there is subtle difference between denominations of different currencies. If you have automatic white balance or automatic tracking white, as we described previously, it is possible that the indoor source of light might be completely unknown to you, or it could be out of range of what the camera can do. And often what happens is if the camera sees anything white, adjust itself to that white if it is automatic tracking white. Balance circuitry, and as soon as you remove that white because of the light reflectance from other sources which are brighter but not as white as the white paper, the color may correct again. So you may have a situation where when you need a very accurate color reproductions, the color actually may fluctuate, and that's not due to bad lighting perhaps, but it's just simply because the white balance tries to catch up with the changes of the color depending upon what the camera sees. So one practical suggestion that in systems like this you may be better off if you know there is a particular type of light like incandescent, which is about 3200 Kelvin degrees, to actually manually set the camera to indoor white balance, which will lock it on 3200 Kelvin degrees, and then you don't have fluctuations of the colors. If there are different scenes observed by the camera, and the color of the money perhaps, if you're trying to observe, will be constant, and that might be very important for a project like that. Anyway, going further up in the color temperatures, we are getting close to 4000 Kelvin degrees. Before that we have about 3800 perhaps Kelvin degrees for 1 hour after sunrise. Then about 4000 Kelvin degrees is simulated, produced by clear flash lamp with metal filament. Over between 4000 and 5000 Kelvin degrees, we've got natural 2 hours after sunrise color temperature. Noon light is just below 5000 Kelvin degrees. And the man-made side in this color range would be white cool fluorescent lamps, for example. They could be around 4600 Kelvin degrees. And then we're getting to an important color temperature of about 5000 Kelvin degrees. This is the color temperature where in man-made domain we have some LCD displays that can produce 5000 Kelvin degrees. This is a display that you can use it for nighttime reading, where the human brain prepares to go to sleep by looking at warmer colors. It's kind of simulating sunset in a way. So a bit of a yellowish color compared to the normal color temperature of LCD, which could be around 6500 Kelvin degrees. Temperatures between 5600 and 6000 Kelvin degrees. That's typically for daylight blue flash bulbs, typically used in photography, and of course electronic flash, which is like a camera flash. Now, the 5600 Kelvin degrees is an important, again, color temperature for us in CCTV, because similarly to what we had indoor white balance color temperature preset on most of the cameras of 3200 degrees. We now have 5600 degrees to be the outdoor white balance color temperature, with the similar intentions that you don't change it based on what camera sees, with the changes of the appearance of objects with different tonality, but it's actually fixed to 5600 Kelvin degree white balance. Going further up in the color temperature scale, we have a very important color temperature number of 6500 Kelvin degrees. This is actually used in the reference of color temperatures. It's called D65 color reference, and this is actually some daylight lamps in photography, and majority of LCD displays would have this color temperature, which is 6500. 7000 Kelvin degrees corresponds to about light from overcast sky, 8000 light from bright overcast sky, and we've got somewhere between 8000 and 9000 Kelvin degrees. Some professional photographic lights may have color temperatures of nearly 9000 Kelvin degrees, and also some professional monitors for specific video editing or calibrated instances can have about 9000 Kelvin degrees. This is about the highest that human-made source of light can have. And then we've got in nature about 10,000 Kelvin degrees is light from hazy sky. Anything between 10,000 and 28,000 is light from different types of sky. Typically light from clear blue sky is about 15,000 Kelvin degrees, and as we go northern clear blue sky would be between 20,000 and 30,000 Kelvin degrees. Now you notice that this scale is not linear, it's tried to be logarithmic in order to show you all the important temperatures, and logarithmic is the way human eye sees, so the intensities of light we see with our eyes are also logarithmic in terms of color temperatures as well. So this graph shows the scale in that fashion.